we are going to be graphing exponential functions today, and then we're also going to be solving like real world problems using interest formulas that we use with our exponential functions. Okay, so the first thing that we're going to look at is just a basic exponential function, just to remind you what that is. So an exponential function is called an exponential. It's called exponential because the variable's in the exponent. So that's your clue that it's exponential. You've got your x in the power. Okay. The b is our base. And our exponential functions can be growth functions or decay functions. Let's see if y'all remember. It's going to be a growth if the base is bigger than what? Yeah, 1, if it's bigger than 1. So for growth, the base is bigger than 1. Because you're going to be multiplying each time by something that's bigger than 1, so it's going to be getting bigger. Like times 2, times 3, times whatever. Over and over and over again, it's going to be getting larger. But what would the base need to be a decay? Yeah, from 0 to 1, because that would be like a fraction of what you started with. If I kept multiplying by a half, it's taking what I started with and cutting it in half, and then cutting that in half, and then cutting that in half, and cutting that in half, and that's going to make it smaller. So for decay, our base is between 0 and 1. When the base itself is just 1, it's not an exponential function, because what is 1 to any power? Yeah, 1 raised to anything is just 1, so that would just be a straight line. So that's not going to be an exponential function. So it's only for things that are not 1 for the base. Okay. So we are going to graph just like the basic one so that you can see what it looks like to remind yourself. Then we'll do transformations and point out the important pieces of this and how we shift them around. But y'all will be probably good with the shifts because they're similar to what we've done before. So we'll just graph a basic one. Is this growth or decay? It's a growth, right? Because the base is bigger than 1. The base is 2. Now let's make a table of values, and we'll plot it. All right, so we're going to plug -2 in first for the power. 2 to the -2. Remember, a negative exponent makes it go to the bottom of the fraction. So 2 to the -2 is going to be 1/4. When you see a negative exponent, that says move to the bottom, and 2 squared is 4, so that got moved down there. So in the same way, 2 to the -1 is going to be 1/2 to the first, or just 1/2. 2 to the 0 power. Anything to the 0 power is always 1. Thank you. And then we know 2 to the first is 2, and 2 to the second is 4. -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. I call this the doubling function because it's going to double. Your number doubles every single time. We started at 1, and then it doubled to 2, and then 4, and the next number would be, what would be our next number? 8, right? And then the next one would be 16, and then 32, because we're multiplying by 2 each time. So it's going to shoot up pretty quickly. We're never going to get below the x-axis with this one because 2 to any power is always a positive number. You can't turn it into a negative number by raising it to a power. So since we are not going to cross this or get to 0, we've got an asymptote that goes along at 0. Okay. So for this, our domain is all real numbers because you can plug any number in, but our range is only the y values that are greater than 0 for this. Okay. It's important to note your y-intercept. If there is not a number in front of your base, your y-intercept is always going to be 1 because any number to the 0 power is 1. So just remember that when you're looking at graphs, that the y-intercept is going to be 1 if we don't have numbers in the front or if it hasn't been shifted around. I do want to mention the natural exponent function right now. It graphs very similarly to 2 to the x because the variable, not the variable, the number that we use in our natural exponent function is close to 2. But it's just one that has special properties when we're talking about interest and other things with exponents because it gets its own variable name, just like, or its own letter, just like pi gets its own letter. So does our natural exponential. It has its own special letter. Does anybody remember what that letter is from last year? It's a vowel. It's a natural exponential function. E, yes, for exponential, right? I don't know if that's why they named it like that, but we use it in this. So that's the natural exponential function. Just has special properties, but E is around 2.6 or 2.7, so it's a growth as well. Yeah, let me see what it exactly is. So let's see. 2.718, blah, blah, lots of things. It's also irrational and it never repeats the variable or the decimal stone. 2.718, da, 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 da. So when we graph it, we just know that it looks similar to 2 to the x. It's a little bit higher when you're going to 1 than 2 to the x, but similar to that. Okay. So don't get like scared if you see an E in a problem. Just know that the E, that this number is 2.718 for that. Okay. All right. And let's talk about some of our transformations and how that's going to change our graph. Sorry, this is not letting me hit the extend button. There we go. We will do some graphs that shift all around the page, and we'll talk about those in a second. But the first transformation that you'll see a lot with exponential functions is just to have a number in the front of the base. And the number in the front of the base is going to be our starting value which will correspond to our y-intercept if we're going to graph it. So if we see this, f of x equals, and we have a number in front of our base, if there's no other shift, if it hasn't been moved left or right or up or down, this is your initial value, okay, which on your graph corresponds to your y-intercept. So we can just do a rough sketch of one. We don't have to make a table of values or anything. Okay, that's better. Let's pick an initial value. What initial value does someone want to do? Y'all can hold your hands up. Just give me a number that's the 3. Okay, so we're going to graph f of x equals 3. And then how about let's do a, you want to do a decay function? You want to cut it in half? Cut it in half each time? Okay. So let's do 3 times 1/2 to the x. That means we start with 3, and our number gets cut in half every time. So we're going to graph that. I'm not going to do any negatives because I don't need any in this problem. So just looking at this, we can see our initial value is 3. That's going to be our starting value. That's our y-intercept. And this tells us what's happening to our numbers. So our numbers are getting divided by 2 or getting cut in half for each x value that we scoot over. Okay. So if I move to 1, what would my y value be? I'm cutting 3 in half. So what is 3 if you cut it in half? Yeah, 1.5. So if you're over at 1, you'll be at 1.5. And if you cut 1.5 in half, you'll get 0.75. Yeah, 0.75. Then we cut 0.75 in half, and you get 0.3750 or 0.375. So that's getting cut in half. Then it's getting cut in half. Are we ever going to get to 0? No. If you take something and cut it in half, it's going to get smaller and smaller and smaller, but you're always going to have a little teeny tiny bit left. Okay. If I backtracked 1, this is also good to think about. If I was started at 3, that's my initial value for my y-intercept. But say I went to -1, what would be my value if at -1? It's going to be 6, right? Because I'm cutting in half every time that way. So if you think about going to the left, those numbers are doubling each time for that. So if you wanted to go back 1, that's fine too, just to see. But this is what a decay graph looks like. It's just the reflection of a growth on your y-axis, if you're wondering about that. So that would be our y-intercept. That tells us what happens each time. Okay. All right. So now for our main big shift around the graph transformations, just a reminder of how you've done that before, and we all have done all of our transformations and where they move and all the things. Let's see. F of x equals, we could have a plus or minus in the front and have our a value. We'll have our base. It can be to the x minus h, and then we got a plus k at the end. We can also have a negative with the x up here. I'm going to put the parentheses around it. There could be a negative up in the front. That could happen. So y'all help me out with all the different moves. Plus k at the end, that's going to shift it which way? Up and down, right? So this is up or down. The x minus h part up there with that value, that's going to go left and right. A left is a plus, a right is a minus. You have to make sure that when you're figuring out if it's going left or right, that if there's something in front of the x, that you've pulled it out of parentheses and factored that whole thing out. All right, remember we said this a value here is going to be our starting value or our initial value relative to where we had to move the graph. So it won't be the y-intercept if you shifted it around, but you'll figure out like where you shifted it in height-wise and where you moved it over, and then you would go up that much from there, like wherever it would be from the origin. That's how much that goes up. And a positive is going to be going like above the x-axis like that, like the ones we've done. So positive can either be a growth or it could be a decay like this. These are both positive graphs. Negative are going to be flipped over. So this is a negative growth, and this is a negative decay. I'm not going to write that on there. So this is a positive growth and a positive decay. This is a negative growth and a negative decay. That makes sense to grow negatively. Seems kind of weird. Like you're going towards negative infinity, but the space between the x-axis and your line is getting bigger as you move along. So that's a growth. Decay is when it's getting closer to the x-axis as you move to the positive direction. Right. And if you have a negative up here, I don't think I gave you any of those on your homework, but just in case you ever see it, it's going to reflect over the y-axis. So whatever how you would normally draw it with that base, it flips it over the y-axis. So if your base was like 2, it would switch to 1/2. If your base was a third, it would switch to 3 because it's got a negative power, and so it makes it the reciprocal and switches from growth to decay. Okay. Let's graph one of those, and then we'll talk about our word problems. Let's write down all of the things that are going to happen. Our negative tells us it's going to flip over the x-axis. The x plus 4 in the top means it's shifting which way? Four to the left, right? So this is going left 4. And this minus 2 at the end says we're going down 2. Okay. And we have a base of 2, so we are doubling. And these I'm not going to ask you to be super precise. I do want to see where your asymptotes are and where your normal y-intercept would have gotten moved to. Okay. So I kind of like to start with that. So with this graph, it's just going to be 2 to the x, and our normal y-intercept is at 1. We didn't have a number in the front. So I'm going to go ahead and put where that normally was. So that would have been our y-intercept. But where did we move? We moved 4 over and 2 down. So our new y-intercept, well, y-intercept, but where that point got moved to was 4 over and 2 down. I'm going to do that first. I know I'm going to have to go through this point. Okay. I'm shifting 2 down, so I would normally have an asymptote that crosses at the x-axis, but I'm moving that asymptote down to.
Why was the y-intercept 1 for the first one before it was
Because
changed?
there's no number that's in the front, so that would have to be where it would need to be. But for this one, I forgot about the fact that we're going to be flipped over as well. So the y-intercept wouldn't have been at 1 because I forgot that it was negative. So just scratch that. It would have been at -1, right? Because it would have been flipped over. So that's what it needed to be. So it would have been -1. Now let's move it over 4 down 2. Here we go. Yeah, that makes more sense. So over 4 and down 2. So we're going to have to go through this point here. And we know that it's a growth function. So it would have normally looked like this, but we're flipped over the x-axis. So instead, we're just going to sketch it this way. So originally, this would have been, this is 2 to the x by itself. This is 2 to the x. So if I take this, shift it over 4, down 2, and then flip it over, it looks like this. If you're taking it here, move it down, and then flip it. So over 4, down 2, then flip it. Okay. Most of these will just be about like recognizing, should it be right side up, upside down, and would it move to the left or to the right. You won't have to graph any like by hand. You just have to recognize where it got moved to. All right, we are going to talk about 3 different formulas. There's your real world math. Some people always complain that we don't ever do things that talk about the real world, and here we go. This is like the most real worldy we're going to get all year. There might be some stuff later on. So we have 3 separate formulas that talk about interest or things that are growing or decaying or increasing or decreasing over time. And they have different situations that we use, like one for one for something else. And so I'm going to write all 3 of them down and then write when you know to use them so that you can have them all written together. Okay, so we've got our basic one, which is this. You can make a little chart with all 3 of them. Sometimes you use a little a, or you could use a p. Maybe I'll put a p there. They mean the same thing. Do any of these formulas look familiar to you? Maybe the first one? Okay. And I put a plus, but we could always have a minus in these problems if we are decreasing. So if it's decreasing or depreciating or decaying, you're going to have a minus instead of a plus. So you might want to put a minus underneath. You don't do both. You just have to pick depending on what the problem says. Okay. Of t, that's always going to be our final value. So that's the same for all of those. Our little a or our p, that's going to be our initial value or our principal. If you're talking about money, principal is what you invest. So the little a or the p, that's the initial or principal. It's what you start with.
Is that an N at the top?
Yeah, these are ends. Our R value, what do you think the R stands for? We're talking about interest. It would probably be the
rate.
Right, yeah, R is the rate. They're going to give it to you most likely in a percentage form. So if it's in a percentage form, you need to turn it into decimal form, okay? So if percent, you need to change to decimal. And T stands for time. Okay, so all of these things mean the same thing in the other two, but this has got one other variable in it. This N in our second equation is going to mean the number of times that our amount that we've invested or what we have in the bank is compounded per year. The number of times compounded per year. Okay. And in the third equation, the little e is just e that we talked about earlier, our natural exponential number. And in your calculator, it's on the left-hand column. You have to hit second to get the e on there. So now I'll tell you when we use each specific one, and then we'll put them into practice. This one didn't have any new things to know about it. Okay, the first kind is if there is no mention of compounding at all. This isn't anything that does anything fancy. It's kind of like something is increasing at a rate of 75% a year, you would use this formula, okay? Or something is doubling, you'd use this formula. Or something's being cut in half, you'd use this formula. If it's just like per year, one time over and over and over, there's not anything fancy going on. So that we use this when there's no mention of compounding. We use the second one if they tell us that it compounds a certain number of times per year. We can extend this to where it's like per month or per decade or whatever, but all the ones that we're going to do are going to be per year. And the last equation is compound continuously. So if you see the words compounded continuously, we're going to use this last one. So does anybody have any idea of what compounding means when we're talking about finances or interest? Or is that kind of foreign to you?
Compound is the initial value start, right? What you're going to add to?
No, compounding means like once, if you have money in the bank and you're letting it sit in there for a couple of years or something, if we were using our first formula and that was the setup that you had, at the end of each year, you would get a tally of interest, right? You'd see how much interest you made in that year, and then it would get put into your account, okay? And then the next year, you're making interest off what you had in there the first year plus the interest that you earned. And then the next year, you're making interest off of the two sets of interest that you got and your initial value in there. So it's adding the interest back into your original amount, and you're making interest off of your interest. So compounding is taking it and making it where the interest is now part of the investment that is earning interest on it. So if we only compound it once a year, you're not making money on that interest at all during the year. But if we do it like 12 times a year or monthly, your interest gets added into your principal, and then you make more money on that each month. And then that interest gets added, and that interest gets added in there. Compounding continuously means all of the time your account is making money, and the interest is always going back in. It might just be like pennies on the dollar or even partial cents that you're making because your interest rate is so low, but it keeps going back into your account to make money on that. So compounding continuously always yields you a higher amount if you have the same principal rate and time. So if you have it continuously, you're always going to make more money, but not all accounts have that set up. Some of them only do it quarterly or monthly or biannually, and some are only yearly. So the yearly ones, we don't have to factor in how many times a year for that. Okay. So we're going to do a couple setups, one of each of these problems, just so you can kind of see what they are. Y'all are going to help me out. We're just going to make some up. Just so you can kind of see how these all go. All right, so for our first one, we can just do any kind of situation that we want. How about, you want to talk about a population that's growing? Okay. Or do you want it to be decreasing? It doesn't matter to me. We can take a poll. So let's say that our population, someone tell me what our population is.
25.
25? 55? 25 plus 55 makes 80. Okay, so our population is 80. 80 what? 80 squirrels, 80 fish, 80 birds.
80 cows.
80 cows. So we got 80 cows. Okay. Let's say that, do you want the number of cows to be going up or number of cows to be going down?
Down.
Okay, so we are decreasing. Let's decrease, and let's say we're going to decrease at a rate of, what percent do you want to decrease?
3.
Okay, we're decreasing at a rate of 3% per year. And we want to know how many cows will we have left after blank years? How many years do we want to see? 4 years, okay. So we've got 80 cows. They're decreasing at a rate of 3% a year. We want to see how many cows are left after 4 years. So we didn't mention anything about compounding, so we're going to use our situation up here. So our final, we're doing 4 years. It's going to be, our initial value was 80. We'll have 1. We always have a 1 right there. Is this a plus or a minus? It's a minus because it's decreasing. And 3% is 0.03. Remember, you have to move your decimal 2 places. And that's going to be raised to the 4. So if we type that in, how many cows will be remaining after 4 years? We're going to have 70 cows left. It says 70.8 when you type it into the calculator, but can you have 0.8 cows? No, when you're talking about things that are living like that, we always round down. We're not going to have an 0.8 cows. All right. One thing that's neat to notice on this is if we're losing 3% per year, how much are we keeping? If we're losing 3% a year, how many are we keeping per year? What percent? We're keeping 97% per year. So if you do 1 minus 0.03, that is 0.97. So if you went ahead and subtracted it, well, the number that's in here is the number that you're keeping. We're keeping 97% of them. Okay. Just to think about that. If you saw that number in there and it wasn't written in the 1 minus form, that you would know that you're keeping 97%, which means that we were losing 3%. All right, so now let's switch over to some money problems because we're going to start compounding, so we'll talk about money. Let's invest some money. How much money do you want to invest?
$20,000.
20,000. Good. We're going to invest 20,000. And hopefully our investment is going up, right? We are investing 20,000. It's sitting in the bank. It's making interest. We don't really have to do anything for it. So what do we want our interest rate to be? 5%. 5% be good. 10% would be awesome. Interest rates are normally like less than 1%, if that. Right now, we're not really getting that great return. But let's say that we were in a fantasy land and we had a 5% interest rate. And we're compounding it, you want to do 4 times a year? So we're going to say quarterly, which means that it's 4 times a year. And how long do you want this to sit in the bank? Let's go with at least 20 years. Let's use something more than 20. So we'll see how much money we can get. Someone give me something more than 20? 22? Okay. So we're going to have this be in the bank for 22 years. So if you invested 20,000 the day you were born, yeah, like you had that money the day you were born. When you finish college, let's see how much money you'd have in the bank. So here we go. So we're going to go A of 22, so it's 22 years. Our principal is 20,000. And then 1 plus 0.05 over 4 raised to the 4 times 22. Because you've got to put that in there for this formula. So 20,000. 1 plus 0.05 over 4 raised to the 4 times 22. Oh, nice. Anybody do it? See what it was? You're going to have $59,675.05. So after 22 years, your money has tripled. How about we invest that same amount, but let's do it in a continuously compound account rather than compounding quarterly, and let's see what the difference is. So go ahead and write out what that would be set up. So we're going to use the same situation, but not quarterly. We're going to do continuously instead. So we'll say A of 22 is 20,000 E to the RT, so 0.05 times 22. Let's see how much more we would have got. It's probably going to be pretty small, but it'll be more than it. All right, has anybody typed that in? is $60,083.32. So it's $400 more that you got doing it the second way. Okay. So in this lesson, graphing, shifting graphs around, figuring out the initial value, and then regular interest formulas, compounded different times per year, and then compounded continuously. So look for those keywords to figure out which equation or which formula that you should use for them. Any questions, anything? Okay, you feel okay with this? You think you can handle it? All right, well, you have 35 minutes. There's a good chance that you can finish it all during the class. You do not